solving trigonometric equations. So our objective here, we want to solve trigonometric equations and applications, both analytically or algebraically and graphically. Well, we've been through a lot with our trigonometry and our trigonometry knowledge, and here's a recap of it that may or may not be applicable, depends on the problem. We know our sine, cosine, and tangent. We know our unit circle trigonometry values. We know the 8 basic trigonometric identities: sine, cosine, tangent, cosecant, secant, cotangent, tangent, cotangent. We know our 3 Pythagorean trigonometric identities. We also learned the sum and difference formulas: sine, cosine, and tangent. We learned the double angle formulas: the sine of 2 alpha, cosine of 2 alpha, and the tangent of 2 alpha. And finally, we learned our half angle formulas for both sine and cosine. That's a lot. Of course, not every problem is going to involve each of these every time, but we want to know that we have these at our disposal as we work to solve trigonometric equations. All right, let's do some solving. And then we're going to also solve these graphically to see them using Desmos. Okay, example number 1. Solve the equation 2 times the cosine of x plus 1 is equal to 0. Solve it analytically using identities when necessary for exact values for the values of x from 0 to 2 pi. Well, this should tell us right here that we're going to be in radians because we're going from 0 to 2 pi, and we're going to solve graphically to check. Okay, so let's first solve it analytically, or what I also call algebraically. So we have our equation 2 times the cosine of x plus 1 equals 0. All right, so let's get ourselves, there's our x, so let's get everything else out of the way. So I'll subtract 1 from both sides. And 2 times the cosine of x now equals negative 1. I'll divide both sides by 2. That, of course, is a 1. And I have that the cosine of x is equal to negative 1/2. Well, this is a unit circle trig identity. When is the cosine of x equal to negative 1/2? So let's take a peek. Here is our unit circle. Again, cosine is the x value. When is the x value? Negative 1/2. Well, so look over here. The x value is negative 1/2. X is negative in quadrants 2 and 3. So we'll take a look in quadrant 2. X is negative 1/2 when cosine is 2 pi over 3 in radians. And again, x is negative 1/2 down here. I hope I'm getting you so you can see it. Let me go like this so you can see it. Down here, right there, when the angle is 4 pi over 3. So there are 2 places where the x coordinate is negative: 2 pi over 3 and 4 pi over 3 between 0 and 2 pi. So our answer says when x is equal to 2 pi over 3 and when x is 4 pi over 3. Okay, let's solve that graphically. Graphically just says, let me write down the word graphically. Let's let y equal the left side. So y is equal to the 2 times the cosine of x plus 1. And let's let y equal the right side, 0. This, of course, is a cosine curve. This, of course, is a straight line along the x-axis. And where they intersect between 0 and 2 pi will be the answer. And we think it's going to be right here, 2 pi over 3 and 4 pi over 3. Okay, to Desmos we go. I'll get it set up, I think, here. Okay. All right, so first off, excuse me, we're in radians. I'll go to my, my tool button top right, And we'll notice that I'm in radians here, so that's a good thing. I always need to check that, and I sometimes forget. Okay, so our left side says y is equal to 2 times the cosine, that's a function. So we'll go to the functions under trig, and we'll do cosine of x, close the parenthesis, and we'll add 1. We'll notice that the adding 1 shifted the cosine function up 1, or shifted twice the cosine function up 1. Okay, we'll go here back and we'll do a y equals 0 so that we see the horizontal line. So there's y equals 0, and we want to be between 0 and 2 pi. Well, mine's already kind of there. 2 pi, of course, is a little more than 6. So we're going to go from here to here. And we want to know the intersection points. Well, there's one and there's one. Those are the two right there, between 0 and 2 pi. I think you can probably see 2 pi right there. Yep. Between 0 and 2 pi, we have 2 intersecting points, so we have 2 solutions, 2 pi over 3 and 4 pi over 3. Very quick to solve that graphically. So we were correct with our analytical, with our algebraic work. Okay. Let's take a look at another one that's a little bit more complicated. Why not? We've got the skills. Solve the equation 2 times the cosine of x squared minus 2 times the cosine of 2x minus 1 equals 0. Analytically, for values of x between 0 and 2 pi. So we're again in radians, and we're going to solve graphically to check. Okay, so let's get our equation in here. Got a little ladybug on my desk. Let's get the ladybug off my desk. 2 times the cosine of x squared minus 2 times the cosine of 2x minus 1 equals 0. Well, let's see here. I think first things first, let's move the 1 over. And of course, that's a 0. So now we have 2 the cosine of x squared minus 2 times the cosine of 2x is equal to 1. Now, a common factor of 2 can come out of here. Okay, so 2, again, we're trying to get x isolated, so we got to find some way to get these cosines together or some way to combine those two. But a common factor of 2 can come out, and then it can get moved over to the right side using division. So we'll divide left side and right side by 2, and we'll have the cosine squared of x minus the cosine of 2x is equal to 1/2. Well, that's getting better. Okay, let's recognize we have an identity. The cosine of 2x. Okay, if I go back over to here, we'll notice cosine of 2x is equal to, one of our identities says take a look at this, and we can rewrite this as the cosine squared of x minus the sine squared of x. So this will become the cosine squared of x minus, I'm going to replace the cosine of 2x with this one right here. And as you might imagine, this just takes practice. Okay, here's cosine of 2x, cosine squared x minus sine squared x. So I'm going to subtract cosine squared x minus sine squared of x. So replace that with the equivalent. This is the cosine double angle formula replacement is equal to 1/2. Well, that worked out pretty well. This negative can then distribute, and I have cosine squared of x minus cosine squared of x. Well, that's 0. And then I have a minus a negative, that's a positive. The positive sine squared of x is equal to 1/2. So that worked out real well. I had a couple of different x's. I replaced this with its double angle equivalent, and I got rid of the cosine squared of x, and I'm left with just a sine squared of x. I can square root both sides, and I have the sine of x is equal to positive or negative, don't forget, the square root of 1/2. Okay, this can be manipulated. This is plus or minus 1 over the square root of 2. The square root of 1 is 1. The square root of 2 is square root of 2. And then I can rationalize the denominator by multiplying both numerator and denominator by the square root of 2. You've done that in the past. And we have the square root of 2 over, well, root 2 times root 2 is 2. And this is one of our known values. When is the sine of x? Root 2 over 2. Okay, where's my unit circle? Okay, when is the sine of, whoops, I forgot. There's a plus or minus there. My mistake, I bet you caught that. I forgot the plus or minus. So this is the plus, the positive or the negative, root 2 over 2. All right, so when is the sine of x equal to positive or negative root 2 over 2? Well, that's in all four quadrants, positive or negative. In the first quadrant, the sine, of course, is the y value. It's right here, root 2 over 2 at pi over 4. In the second quadrant, the y value is again positive. There's my sine, y value, root 2 over 2, and that is 3 pi over 4. As I go into the third quadrant, my y value is negative. That's okay. We're taking positive or negative. Here's the negative of root 2 over 2 at 5 pi over 4. And as I continue along, I get another negative root 2 over 2 as a y value here, which is 7 pi over 4. So I have four answers between 0 and 2 pi. We'll also see that, of course, in our graph. So we know from our unit circle, whoops, if I could spell circle, C-I-R-C-L-E. Okay, we know that we have x is equal to pi over 4 because that gives us a positive root 2 over 2. X is equal to 3 pi over 4 because that also gives us a positive root 2 over 2. X is equal to 5 pi over 4 because the sine of 5 pi over 4 is negative root 2 over 2. And finally, x is equal to 7 pi over 4 because the sine of 7 pi over 4 is also a negative root 2 over 2. Okay, let's do this graphically. So let's take a look at our equation. Left side has got a lot going on, so I'll set y equal to the left side. The right side is just 0, so I'll do a y equals 0. That'll draw my line on the x-axis, and we'll see where those two intersect between 0 and 2 pi. Okay. So we're solving it this way. I guess in this case we're checking it this way, but we could also solve it this way as well. All right, again, I'm already in radian mode. Left side, y is equal to 2. Okay, cosine squared. I like to go to the functions, and I like to choose cosine of negative 1, and then I back it out, and I delete the negative 1, and I put a 2 in there. That's just one way to do it. As opposed to the inverse cosine, I just take out the inverse, and it already has the exponent. So this is cosine squared of x. Let's close that parenthesis. Okay, minus 2 times the cosine. Go back to my trig functions in cosine, and we have 2x. Close that up, and my equation said minus 1. So there is the function on the left side of the equation. The right side is just 0, so y is equal to 0. And there you have it. So we can see, again, we're looking between 0 and 2 pi, which is a bit more than 6. So we're going from here to here. If you want me to let's see here, I can kind of go that way a little bit. And we want to say, okay, where do these intersect? Well, they intersect there and that's pi over 4. We already noted that one. They intersect here. That's quadrant 2. That's 3 pi over 4. We had that answer analytically or algebraically. Intersect here. That's 5 pi over 4. And finally, they intersect here at 7 pi over 4. Okay? And so those are the four answers we got algebraically between 0 and 2 pi, which again is right around here. Okay? So same, looking good. All right, I have 2 more examples. Give me just a moment to get myself organized. Sometimes I'm more organized than others. Okay, let's see here. Okay, straighten out the paper, get it where it's supposed to be. I think I'm good. Okay, solve the equation 4 minus 3 times the cosecant of x squared equals 0. We're going to solve it analytically or algebraically. We want to again be between 0 and 2 pi, and we'll solve it graphically to check. Okay, let's see here. So I have whoops, I think I might have made a mistake in my paper. We're going to find out if I can get this one right or not on the fly here. 4 minus 3 cosecant squared of x equals 0. Okay, well, I'm going to add 3 cosecant squared. I'm going to make this positive. So if I add this to both sides, I'm going to have 3 cosecant squared of x is equal to 4. So I added this piece to this side, but I just wrote it first, so my x is on my left side. And of course, now I can divide both sides by 3 to get that cosecant squared of x by itself. And here I have cosecant squared of x is equal to 4/3. Well, cosecant squared, we know, is the reciprocal of sine squared. So I can rewrite cosecant squared as 1 over the sine squared is equal to 4/3. Okay, and if you want, I can flip-flop both sides. That's not really a mathematical. Basically, I'm just multiplying. You know, I'm either cross-multiplying and dividing, or I can multiply both sides by the sine squared and both sides by the 3. It all works out the same way. If 1 over the sine squared is 4 over 3, then the sine squared over 1 is 3 over 4. Okay? And then, of course, we can square root both sides. And we have the sine of x, again, is equal to positive or negative the square root of 3 over 4. Don't forget, when you square root both sides, you have 2 possibilities. A little bit of work on this one, just a touch. This is plus or minus, well, it's the square root of 3. That's the square root of 3 is the square root of 3, but the square root of 4 is 2. So I have the positive or negative root 3 over 2, and that takes us right back to our unit circle. When is the sign, what x values has a sign that's either positive or negative root 3 over 2? Well, of course, we're in all 4 quadrants. The sign is positive in quadrants 1 and 2. The sign is negative in quadrants 3 and 4, so we're going to have 4 answers. When is the y value equal to root 3 over 2? Where's my chart, my unit chart? Okay. So in quadrant number 1, root 3 over 2 is right here. Okay, so there's the sign. So pi over 3 is an answer. In quadrant number 2, here's the y value of root 3 over 2. That's 2 pi over 3. In quadrant number 3, here's the negative root 3 over 2, and that's at 4 pi over 3. And in quadrant number 4, here's another negative root 3 over 2, and that's at 5 pi over 3. So we know our answers. Again, looking at our unit chart, x is equal to, we have 4 possibilities. Pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Okay, so that's our algebraic solutions or analytical solution and solution method. Let's solve graphically. So our left side is going to be y equals, it's on the left here. We're back at 0 for the right side. We set the left to equal and if we set the left to y and the right to y, where they intersect will be the answers, and we should get 4 between 0 and 2 pi. Okay, back to here. Let's go ahead and delete these two. Okay, so this first one says 4 minus, so y is equal to 4 minus. We want the cosecant of x squared. Well, my trig functions, Desmos has cosecant here. It also has the cosecant to -1. And I like to use that -1, that inverse, because then I can go back with my arrows and I can simply delete the -1 and my cursor is still in the exponent and put a 2 in there. It's just one way to do it. And so this is, whoops, I forgot the 3 in front. Let me tap there and put the 3 in front. It's nice I can correct that. And then I have an X in here. Close it up. And there, whoops, there is my, wow, that's pretty, looks like a pretty tall, that's quite a tall function as that comes in. I must go way down there. I'm just taking a look at this, and that obviously is something. Okay, well, we're going to focus on the y-axis, thank goodness. So I'm going to come back in here and look at the y-axis. There we go. I'm focused on the y-axis, and I'm focused between 0 and 2 pi. So I'll kind of extend it. So there we go. I'm on the y-axis. Let's put that in there, by the way. Y equals 0. That's the right side of the equation. I went from 0 to 2 pi. Again, a little more than 6 over here on the right. Where do they intersect? We can see 1, 2, 3, 4 points of intersection. That's what we calculated algebraically. We can tap on those 4 points, and we can see that pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3 was exactly what we got using algebra. All right, as I said, it often is very quick to solve these things using the graph. Just make sure you're in radian mode as necessary. Okay, let's see here. The example 4, our last one, the acceleration due to gravity in meters per second squared varies with latitude, approximately given by g is equal to 9.7805 times the sum of 1 plus 0.0053 sine squared theta, where theta is the latitude in degrees. Uh-oh, we gotta make sure we're in degrees with this one. Let's note that. Graph this to estimate theta for g is equal to 9.8000. Notice that maximum latitude is 90 degrees, so we're not going to go above 90 if that's maximum latitude. Well, let's see here. We're told g is 9.8, so let's put 9.8 in for g. So 9.8 is equal to 9.7805 times 1 plus 0.0053 times the sine squared of theta. Okay, so I simply wrote the equation down, but we're told that g is 9.8, so I put 9.8 in for g, and there's my equation. We can solve this graphically. Well, great. Let's let this equal y on the left, and how about having this side equal y on the right, and let's see where they intersect between 0 and 90 degrees. Okay. All right, so let's go back into here. No math at all. In this one, we're just going to make use of our graphing device, in this case, Desmos. Let's get out of these. Okay, the left side was y is equal to 9.8. And that, of course, is going to be a, well, I got to kind of, there's your horizontal line just below 10. Okay, oops, I forgot. I got to be in degrees. Whoops, let's go to here. Go to degrees. Okay, almost forgot about that. Okay, so there's my line at y equals 9.8. My second is a going to be a curve of some sort. So on the right side of my right side of the equation is y equals 9.7805 open parenthesis times 1 plus 0.0053 0.00. Whoops, I forgot the 0. Let's get a point in there. How about 0 point? Point. There we go. There's my point. 0053. Checking my work. That's 2 zeros after the decimal 53. Times sine squared. Back to my trig functions. Again, I like to use that -1 and then just back it off and delete it and put a 2 in there. Okay, where's that 2? The sine of x, we don't have a theta, so we're going to use x, and we're going to close it and then close it. And so here we are, and we got to come up with where these are intersecting. Did I miss anything? I don't think so. Why am I not? Let's see, I got to figure out what's going on here. Sine squared of x, so let's see. The answer is, oh my goodness, I got to really zoom in here. Okay, so as I zoom in, notice that, okay, I'm really zooming in on 9.8. Okay, I really had to come in tight. Notice I'm going 9.75. I'm going by 0.05. So I've really come in tight. And you can see down at the bottom down here, I think, let me just shift it up a touch so you can make sure you see that. Here's 50 on the x-axis, and that's our degrees. So here's 100. So I want to be, I want to be between 0 and 90. I want to be between these two places, 1 point. It looks like it is 37.831 degrees is that one location. Okay, so we come up with one intersection between 0 and 90 degrees. I had to really zoom in to get this. Okay, so 37.83, we'll call that 37.8 degrees. Okay, so estimate theta, and we used Desmos, and Desmos told us that theta is equal to approximately 37.8 degrees rounded to the nearest tenth. That one took a little bit of playing with that calculator and with the graph to come up with it. But they certainly, as we zoomed in, there were two different graphs, and there certainly was an intersection point. So there you have it. A fair amount of work. Of course, this is a lot of practice because all these are a little bit different, so don't expect that you're going to just nail this the first time. It does take a little bit of practice to kind of work with this and see some trends and patterns and maybe some starts and stops as you work to find the answers. And then, of course, realize that graphing it is often a very simple way to either solve and or check your answers.